So today I'm going to talk about PCA for high dimensional heteroscedastic data. This is work that I have done in collaboration with my ex-PhD student, who's now a postdoc at Wharton, David Hong, and my current PhD student, Kyle Gilman. Both of them are outstanding and very interested in all the aspects of low-rank models. So I encourage you to watch their career over the next few years. And then my colleague at Michigan, Jeff Fessler. So to motivate this problem, I want to talk about physical problem that we have seen over the last couple of years. Certainly last summer, the fire season that was out on the West Coast was very serious, and it's happening again now. Okay, so last summer and early fall, fires caused very serious air quality issues around Western United States. And people started looking at data in order to, see what their personal situation would be that day, the next day, maybe predict and try to understand what was happening. The data that were collected and shared online were coming from two different types of sensors. Okay, that's this map that I show over here is actually a map of those sensors in February of this year. Some of them are from the Environmental Protection Agency called Air Now sensors. And these are, you can imagine, pretty high quality instruments that are maintained on a regular schedule and have good sensing characteristics. And then what was very interesting that happened starting last summer was an explosion of commercial sensors that individuals were deploying and agreeing to, hook to the internet and allow their data to be shared through what's called Purple Air, a website that sells these sensors, and then, if you approve, also shares the data that you collect. So all these sensors were collecting the same types of measurements, and they were looking at the same phenomenon, right? But the commercial sensors, of course, are not maintained in the same way as EPA sensors, and are also just not as high quality, have higher noise variance, and different characteristics. Okay, so because of the difference between these two data types, even though they're measuring the same thing, looking at the same phenomenon, people often just looked at one or the other and did analysis on one or the other in order to avoid any issues of trying to merge these data together. Okay. And this isn't just a problem in environmental sensing, it's a problem in many, many modern data problems or data applications. For example, I mentioned this is work with Jeff Fessler. Actually, his ideas started this whole project several years ago in medical imaging. That's his expertise. And he said that, in medical imaging, in particular, model-based imagery construction, we're taking data that we've collected and using it to learn some type of model that we can use to reconstruct future images. And because of the way methods, the assumptions methods typically make, we have to only take data from one machine with one radiation level, meaning one signal to noise ratio, and we can use that data to learn a model. But obviously, ideally, we would love to use a whole history of data where we may have different radiation levels, different signal to noise, different instruments even, and use all that data together to learn, for example, a model of the imaging of the lungs in order to improve that model-based imagery construction. The same problem actually happens in astronomical imaging, where it's not a question of heterogeneity of the instruments, but heterogeneity of how you view the thing you're interested in. So these celestial phenomena you're observing through different atmosphere at different times of night or different nights throughout the year and different years. So trying to combine all these data is exactly the motivation of this work, instead of just looking at data that have, one signal to noise ratio, one noise characteristic, we want to combine them together and do some analysis. Okay. So in particular, hopefully this crowd, like I, had a first question, or a basic question. You could say, okay, if we're trying to combine data and do analysis, how about trying to identify principal components in these data? Okay, so that's what I'll be talking about today, is how to identify principal components or low rank models when you have different quality data. Okay, and in particular, when I say different quality, I'm going to mean something very specific, which is that I have data that should be nearly low rank, but they have additive noise. And that additive noise is of different variance for different groups of data points. Okay, so in this little toy example I'm showing, it's just in 2 dimensions. We have one-dimensional subspace that is generating the data, right? A planted rank 1 subspace. And then we have 2 groups of data, the high quality data, you could say like the EPA sensors. They have a very small additive noise variance. Those are the red data points. And then some lower quality data with a much higher additive noise variance. They're also drawn from the same one-dimensional subspace, but with this higher noise variance in the blue points. Okay, so if we want to find the first principal component of the data here, for those of us who have worked in robust PCA, we can see from this particular data instance that PCA, this pinkish line, is going to be sort of attracted to these blue points that are somewhat outliers. Okay, there's kind of a underlying, not real direction here in this particular instance of data, and PCA is attracted to that because PCA isn't robust to outliers. Okay, so the goal that we have is to create new algorithms, new approaches to this problem that avoid those issues of PCA without throwing away the data or ignoring data as outliers, because actually they're not, they're just very high variance points. Okay, in this low dimensional example, if I ran many different examples, the PCA solution would sometimes be much closer to the truth, but actually in high dimensions, the PCA solution is always biased because of the high variance data. Okay, so let's set notation, and then I'll talk about 2 different approaches we have for this problem. So we're going to have n samples from a d-dimensional space. They're denoted as y1 through yn. We'll put them in a matrix Y. And I'm going to assume the low rank planted model or spiked covariance model, where each one of them is generated from first a low rank component. Okay, so we have rank K subspace U here. We have K amplitudes or singular values. You can think of these thetas. Okay, I also think of them as like the signal energy in a particular direction. Okay, because this U, this is the signal, the planted component we want to discover. And then we're going to assume that they get weighted by some standard IID random weights. Okay, and then we have additive noise. So all of this is standard, right? The additive noise is based on IID standard random variables. And now the difference that we introduce are these variances eta. So for every data point, we may have a different variance that scales the additive noise, okay? Eta 1 through eta n. And it may be at each data point individually, or it may be that we have groups of samples, like in the example of having EPA sensors and purple air sensors. Maybe we have two groups of data. And so if we have L groups of data, then we denote like this, that Ni of the samples have variance equal to sigma I, okay? And so what this means, the terminology for this is that these samples have heteroscedastic noise, okay? And I want to emphasize that we assume that we know the membership of these samples to each group, okay? Like in the case of EPA, we know which ones are EPA sensors, and purple air, we know which ones are purple air sensors, and we're assuming that those have some kind of standard noise characteristics inside those groups, okay? Okay, so I showed you that little toy example, but I just wanted to show some plots to motivate further why just applying PCA directly to this grouped data set is problematic. Okay, so here I have synthetic data where I have 200 samples with a noise variance of 1. And then 800 samples with a varying noise variance. That's what's here on the x-axis, sigma. Okay, so this big group of data has noise variance sigma. Then I just apply PCA, and on the y-axis here I have different measures of how well just regular PCA recovers this planted low rank model, okay? So for example, in this top left plot, we're looking at F hat, which is PCA's output, how well it approximates this planted low rank model normalized, okay? And you can see that, okay, when the really big data sample with 800 points here, when it has a very small noise variance, it does pretty well, okay? But as that noise variance grows, then this error just goes off the chart, okay? And down here, we see the error in recovery for each individual component. And again, you can see, especially for like the second and third component in the planted model, we have very poor recovery as the variance of the second group goes up. And just to sort of give you a comparison, if you were to do, let's say, some kind of robust PCA where you ignore data that comes from a group which is noisier, you could get something like this. So the orange curve gives you, when you only look at this big but potentially noisy group, and this green line, which of course is fixed at noise variance 1, shows you what you get when you only apply it to the small group, which has this fixed noise variance, okay? So we'll revisit this plot later when we look at our new methods. Okay, so we're going to take two different approaches. The first is a weighted PCA approach. Okay, if my PCA, itself isn't working, maybe I can basically scale the data points. Any noisier data point I could scale down and then just apply PCA. Okay, so the benefit of this approach is that it uses vanilla SVD. We can just first find the weights to do the scaling. That's the hard part, but then the algorithm itself, we know, will find the optimal point for this weighted problem, okay? And as you'll see, it's been amenable to some analysis. So we have some results in the high dimensional setting where we can tell you what the asymptotic recovery is, so very analogous to high dimensional PCA results. And in fact, we can use that to derive what the optimal weights are, and that's what I'll tell you about today. The drawbacks of this approach are that, well, it is something to do, but we don't know if it's really the right thing to do. And in particular, as you'll see, it requires knowing some parameters that we wouldn't normally know, or at least estimating them, and our theory doesn't cover, the case where we need to estimate those parameters. Okay. The second approach I will tell you about is a generalization of probabilistic PCA, very natural, where we take PPCA and we just assume now that we have, these noise variances being different for every data point. Okay. So this is a very nice approach because we can use maximum likelihood and we can estimate all the unknowns. All right. It's not a concave maximum likelihood, but it seems like it's probably nice. We're still working on that theory. Okay. But, I think everyone here would be comfortable saying it probably has benign non-convexity, right? We don't have algorithm guarantees or analysis yet. So those are sort of temporary drawbacks, I think. But probably the main one is that we're making assumptions, and in particular normality assumptions here on the different parts of the model. Okay, so I'll, in the rest of my time, talk about these two different approaches. And please feel free to stop me at any point if you have questions on what we're going through. All right. Okay, so the first approach I'll talk about is this one, this weighted PCA. Okay, so we have our data and we're going to look for some weights in order to try to do a better job of recovering the planted subspace. So first, I just want to remind you a little bit about existing high dimensional recovery results for just plain PCA. Okay, so we've known now for over a decade that if you have high dimensional PCA with additive noise, then so high dimensional meaning we have fewer observations than we have parameters or dimensions in our problem. Then if that ratio, number of observations to dimensions, goes to some constant c, so it's not going to infinity, we can't have perfect recovery, right? But we know exactly what the recovery will be in the limit. Okay, so it looks like this. If we have perfect recovery, U hat is the PCA component, U is the planted component, we'll get 1 on the right-hand side, right? So if C is getting very, very large, this will get closer and closer to 1. But it's affected by the noise variance, the signal amplitude or the singular value, okay? And we won't have perfect recovery in this limit if we're in the high dimensional regime. So our first results in this problem were basically translating these theoretical results to the heteroscedastic setting. So we have a very similar result. I'll kind of show some of the details later, but it's a bit complicated, I guess. So basically we have something you can compute, and we know for sure that in the heteroscedastic setting, PCA will converge to this recovery number. And those functions on the right-hand side are rational functions. And yeah, we'll see more details about that in a little bit. But basically, we know how to characterize what PCA does in the high dimensional regime with heteroscedastic noise. Okay. So now what are we going to do to correct for that? We want to do some kind of weighted PCA. Okay, so we want to choose some weight for group 1, some weight for group 2, say if there are L groups up to L different weights. How do we choose those weights? So some very common choices are binary weights, where you try to throw away noisier data, identify outliers, or inverse noise variance weights, a whitening approach to try to put everything on level playing field. And what we asked was, okay, is there an optimal choice? Optimal in what sense? We go back to the result that I just mentioned. So I know what this recovery guarantee is. So what I'm going to do is try to maximize that, right? So I want it to be 1. This is a function of the weights. And so I'm going to maximize it to get it as close to 1 as possible. So now I'm going to give you a peek at those rational functions. Okay, so you can see that each one, A and B, is a, and sorry, this I is with respect to the ith principal component. So in this picture, or in this writing, I just wrote U hat, but you could say with respect to each U sub I, okay? And each one of these is a function of the weights of the noise variances, okay? And the fraction of points in each group. And so as complicated as this looks, they're nice rational functions. And it's actually possible just to algebraically find what the maximum is, okay, of this quotient here. So we looked for the maximum of this with respect to the weights W, okay? And here's what we found. So this asymptotic recovery value of the ith component is maximized by choosing weights. So this WL is the weight for the Lth group. It has the inverse noise variance of that group in it, but it also has a second term, okay, a term which is 1 over the signal amplitude for that particular component that you seek, plus the noise variance again, okay? So it was very interesting, very simple form of this optimal weight. It did not depend on many of the problem parameters like dimension, number of samples, the ratio or proportion of samples in the low or high quality groups. It didn't depend on any of that, but it did depend on these important parameters, the noise variance, which, we sort of thought maybe it's reasonable in some settings to assume what the noise variance is, but also on these amplitudes for every component of your subspace, which of course we wouldn't know and we would need to estimate, okay? So another sort of view of this theorem is in this plot. So remember, I'm just weighting PCA, so I can scale all the weights by a same value, and I would still get the same output from PCA, right? And so if I scale the weights here and look at the signal to noise ratio on this x-axis, then we see that as the signal to noise ratio gets really good, we actually should use the inverse noise variance as the weights, okay? But when the signal to noise ratio is very bad, then inverse noise variance is not aggressive enough, right? We need to downweight very, very noisy samples much more aggressively in order to productively use those data in our PCA estimate. Okay, I'll stop for a minute in case there are any questions. Okay, so let me show you a figure here that just shows you basically what these recovery curves look like, but also the main point of this slide is to show you that, what did I say? I said we decided optimal means we're going to maximize the asymptotic recovery, right? And you could say, well, like we're not ever in the asymptotic regime, so is this really a useful result? And the point of the slide is to show that in not that high dimensions, we are very, very close to the asymptotic recovery. Okay, so let's take a look. What I'm showing here is the inner product of the PCA component with the planted component for synthetic data. synthetic data where I have a square matrix. Okay, so D is equal to N. I have two principal components that are planted, and then two different groups, one with just 20% of the data set and noise variance 1, and the other one 80% of the data set with noise variance 4. Okay, so high proportion of the data, but higher noise variance or lower quality data. And then on the x-axis here, I plot the weights with respect to each other. So I'm normalizing them that they sum to 1. If I don't weight at all, I would then have half here. Okay, so that's like uniform weights or no weighting at all. And this orange dotted line is the asymptotic recovery curve that we proved, okay, for the first component and for the second component. And you can see the green lines are showing the different weighting. So the optimal weights, hit the peak of these curves, okay? And inverse noise variance is right there, very, very close in this case. So orange is the theoretical recovery, but the blue are the mean and interquartile intervals for synthetic runs. Okay, so you can see already here when we have 1,000 samples and 1,000 dimensions, it's very close to the asymptotic recovery. But then when we increase just by factor of 10, so 10,000 samples, 10,000 dimensions, then we basically have concentrated. So this, is a very reasonable thing to choose to maximize. And so these optimal weights are doing that. Okay, so that was the weighted PCA approach. Our second approach that I'm going to describe now is generalizing probabilistic PCA. So probabilistic PCA is going to just impose a distributional model on this planted picture that I showed you before. We'll say that Z, the weights, and epsilon, the additive noise, is IID Gaussian, standard Gaussian, okay? And we seek the maximum likelihood estimator. I'm going to just talk about estimating F here. So some factor matrix as opposed to estimating the components specifically, but we can get the components from F as well. All right, so what does probabilistic PCA do? I'll just show it briefly. We write the likelihood down, and very wonderfully, it is separable in terms of the sample correlation matrix. Okay, so what we've known now for a long time from this beautiful paper is that the likelihood is maximized using the eigenvalue decomposition of the sample correlation matrix. Okay, we use the k principal eigenvectors, and then we shrink the k principal eigenvalues in order to get the maximum likelihood solution. Now, all we need to do for heteroscedastic PCA is replace these etas with eta I, okay? But unfortunately, that means the likelihood is no longer separable. So I can't bring the sum over I here and just look at the sample correlation matrix, because I have this matrix that's multiplying the sample correlation matrix, but that depends, also on each data point I, or at least on each group, in the different subgroups of data. Okay, so we just took the likelihood as it was, non-separable, and derived an EM algorithm to solve for the different things of interest. And in particular, we're interested in estimating the factor matrix F and the noise variances in order to get the best possible prediction for this factor matrix. Okay, so there are no closed form ML estimates from what we can tell for the factor matrix and the noise variances. And in fact, when you fix one, there aren't closed form ML estimates of the other, okay? But in all cases, we just came up with nice alternating ascent or EM approaches, okay? And the result is an algorithm that we called Heteroscedastic PCA or HEPCAT, okay? I didn't include that acronym on here, but anyway, so these plots you might remember from early on in the talk. And what we wanted to do was sort of get the best of all the worlds. If you know, we have really, really noisy data in group 2, maybe we just want to use group 1 and vice versa, okay? And that's what this approach looks like it does, okay? We get some very nice results in terms of error of the factors. And additionally, when we look at the estimate of the variance, it's very good, okay? And the point of this plot is to say that actually it's not only good when you know the block sizes, okay? So this is this problem here where I have 200 samples at noise variance 1, and then 800 samples, and in this case here, we set that noise variance at 4, okay? So if I knew these 200 are in one group, these 800 are in another group, then I get extremely accurate variance estimates. But even when I say, for example, that I don't know which group any data point is in, I let them each be in their own group, then these blue dots show you the noise variance estimate from the algorithm. And you can see, like, for the low variance data, it's very good. For the high variance data, it is somewhat uncertain, but it still does seem to concentrate around the right numbers. Okay, so it's kind of cool and indicative that maybe we can do more even with this approach. Okay, so last but not least, I think I have one more minute and then maybe still time for a question, but I wanted to revisit my original motivation. So EPA and Purple Air both have these data available. So we wanted to take a look and see what we could do using our heteroscedastic PPCA approach, okay? And so this is actually a result for the second probabilistic PCA technique, okay? We took 46 AirNow sensors and 460 Purple Air sensors. Basically, we found 10 kind of surrounding each one of the EPA sensors. And we looked over about 5 days. We took hourly measurements from these sensors. There were some places where many measurements were missing, so we didn't use those hours, but we took some of the hours from those 5 days, okay? And so the dimension D is this 108 hourly samples, okay? And we want to see what happens when we perform PCA on these data. So of course, if I just take a matrix of data and I want to find the best root mean square error, I should do PCA or I should do SVD. That's by definition going to give me the best outcome. So what we did was to take the data and do a train test split. Okay, so we took the data, we took some of it to be training. We're going to learn a subspace from that training data. And then we took some of it to be testing, and we're going to see how well the subspace of the training data that we learn fits this testing data. Okay, so the first thing I'm showing are just the training plots. So this should be, you should, you know, after we talk about each of these, you should say this is what should be true, and you'll see that it is. Okay, so this left plot here, we're looking at the total normalized root mean square error on the training data. So we used that data, and then we computed the normalized square error. Okay, so of course, what should be best is PCA. Okay, so the best error we get from probabilistic PCA. We also get something very close when we run PCA only on the Purple Air data. Okay, so I'll revisit that fact in a minute. Okay, if we run PCA only on the AirNow data, we do much worse. And if we run HEPCAT, this is what we get as the training error, fit on the training data. Okay, So that's all the training data. If we look only at the air now data, okay, so we train on all the data, but then I'm just showing you the root mean squared error only on the air now data. Then of course, PPCA only on the air now data gets the best result. HepCat does, pretty well. And finally, if we look only on the purple air data, again, of course, PPCA on the purple air data does the best. Okay, HepCat does pretty well. So these are all trained, but of course the punchline is test. Okay, so in all cases now, HepCat achieves the best performance or is competitive. Okay, so here on all the test data, so we look at both air now and PA and purple air combined, then HepCat does competitively or a little bit better as PPCA on all the data or just the purple air data. But if you look at the test data of air now, HepCat actually does slightly better than just using air now data to compute PPCA. And the same is true when you look just at purple air. It's competitive or really slightly better. So basically this method is leveraging both of these data sets. It's able to use the air now data and the purple air data to get a better predictive model, low rank predictive model over all the aspects of the data. Okay. So that's the last part of my talk. And what I showed you were two approaches to this problem. We have lots of interest in continuing work to understand, optimization details and give more types of guarantees for our methods. And I have references here. If anyone would like to see the slides later, I'd be happy to share. So thank you. And hopefully there's time for one question.
Thank you very much, Laura. Yeah, there's time for at least one question. And actually, Fernando has one question. Fernando, you want to ask it directly? There's actually two questions. Okay. So Fernando's question is there a probabilistic distribution assumed on the etas in het PPCA?
No, there is not a probabilistic distribution assumed. So we just have it be the parameter here, not a Bayesian approach, just a maximum likelihood approach.
And then there's another question there's another question. Why do we have on average that training error is larger than test error?
That training error is larger than test error on average. It looks kind of higher to me, but I'm not sure, maybe I'm missing something. So certainly these are higher than these, right? Is it this one that, that's being asked, or?
Yeah, thank you for the talk. That was asking. Yeah, by definition, test on average training error is smaller than test error, but it seems these box plots represents the opposite thing. So that's why I'm
but that's what I'm saying. I don't see it. Like, so this one is trained. So here we're at 0.2 and here we're at 0.37. So test is higher.
But not for all the methods. Right?
Yeah, so can you point to me where you're looking, or?
For example, the green plots.
Okay, yeah, I think it's still higher. So maybe it doesn't, maybe it's a question of like, there is one instance where it happens maybe. But this one here is like at 4.3 and this one here is also around the same. So they're about the same. Is there a different place where you mean it, or is that what you meant?
First I thought the green box plot. I didn't look up everything. Yes.
Okay, no worries. It's something to look at though, because certainly it looks like up here, there may be ones, in testing that are better, but we could look at it more carefully.